Yes, so it's working. Let's talk about the 6502 CPU. How many knows this CPU, have heard of it before?
It's from Motorola, no?
Yeah, so not that many. How many has owned a machine containing one of these? I was looking at like 8, 9 people. Okay, so this will be some new things. So originally this was supposed to be like a few years ago. I was floating this suggestion of talking about an emulator I wrote for this machine. This is this talk and some other bits. So I'm also going to talk a bit about actually compiling C++ targeting this CPU, because some things have happened there recently. That's kind of interesting. So this is what it looks like if you pull one out of a Commodore 64 or something. And like the machines that used, they're all from like the late 70s to early 80s. This is like the first machine that used this and was popular. We had one of these when I was very small. The interesting thing with this is the ridiculous hardware. This machine contained 128 bytes of RAM, out of which 5 bytes was actually video RAM. So it's a bit fun but tricky to program for. Apple II was another famous machine, mostly in the US, I think, not as popular here in Europe. And of course, the Nintendo 8-bit also had one of these CPUs. A stripped-down version without decimal mode, but otherwise. But this is, of course, the people here who actually own one of these. I guess this is the machine you probably had. This was very popular here. I, of course, had one. This also contained the 6502, although it was called 6510, but it was almost the same chip, just had an extra I/O register. And so one of the reasons why I'm also talking about this is that there have actually been released a couple of new machines with this chip. Probably because retro computing is popular again, or have always been. So this is the Commander X16. It's taken a long while to get this out, but now you can pre-order it. It's kind of a weird beast. It has a 6502 CPU, but the video hardware is much better than. It doesn't really fit, but it's a fun machine. You can pre-order it for like $350.
That's the 8-bit guy.
Yeah, it's 8-bit guy's machine, yeah. His kind of passion project that he's been working on for many years. And then it's this machine, which is, you can get it pre-ordered for like 800 euros. So I think you really have to like this stuff to order one of these. So this is actually like an implementation of the sort of follow-up to the Commodore 64 was supposed to be called like C65. It never got released, but a few prototypes were floating around, so it was a weird popular machine. And then some people thought that it was a good idea to sort of actually make it a reality. But still, it has a 65C02, which is called now, it's the modern version of this chip. It has a few more opcodes, yeah?
Is it place for floppy disk?
Yes. So I would have kind of rethought that idea, like to keep that floppy there for the new version. Is it really necessary? It probably cost a lot more money to do that, but they were going for some aesthetic here, I think. Anyway, this CPU has some other opcodes and uses a lot less power, but otherwise it's completely compatible. So let's talk about emulation, which is like the, yeah?
What is the CPU used for something in real, except this stuff? Is it still in production?
Yes, it is in production, but I'm not, there are probably small, weird hardware that's still working. I remember, I think what you used, Jonas, you gave me about like keychains that use the CPU.
That was like 15 years ago.
Yeah, so probably not around anymore, with like small keychains with a small screen that actually uses 6502. But I'm sure they're used in some. It's like you can buy the CPU, like so. There has to be a reason, right? It can't all be retro computers. Anyway, so I wrote an emulator for this machine, and but this was a few years ago. And one of the reasons why I did this, I wanted to see if I could actually use this, write it with a bit more modern techniques. So there's a lot of, this is probably the most emulated CPU out there. It's pretty easy to emulate it, that's one reason. But it's almost always in C, lots of macros and if-defs and stuff to be able to sort of make it fast enough. So the idea was like, this should be possible to do with more modern techniques, right? So that was the idea when I started. And okay, so some information about this CPU. It's very simple. It has like 3 main registers. And 6 in total. So A, X, and Y, 3 8-bit registers. A is the general purpose one. X and Y are mostly used for indexing into memory. And then you have the stack pointer, the program counter, and the status register, which are like auxiliary registers. There are only 56 instructions. And each opcode is 1 or 2 or 3 bytes long, and it's uniquely identified by its first byte. This means that starting to write an emulator is very simple. You just you take your code, you read the first byte, okay, what is this? And then you run some code. So an example opcode. So I guess not everyone here is kind of familiar with assembly language, so it might be a bit strange to see this, but this is the instruction that loads something into the A register. And that's why I said there were a lot of opcodes but fewer instructions. So LDA is an instruction, but there are 8 different opcodes implementing this instruction, which you can see from those numbers in the 3rd row. So they all load something into their register. The difference is how it gets this value. So the first version there, it just loads 44 into their register. The following 4 loads from memory somewhere. And when you see the "X", that means load from that address in memory, but add the contents of that register. And the 2 last ones are indirect loads. It loads something from memory, and it looks there, and it takes that address and loads again. So it's going to have to go like 2 steps. That's why you also see the timing there in the last column is how long those opcodes instructions take to execute, how many cycles. And that's also something you need to think about when you write an emulator if you want to calculate the cycles and make sure that it's correct. So this is the kind of things that you need to implement basically when you write an emulator. And the first important thing that you need to decide is if you're going to use a jump table or a switch statement. These are like the 2 main ways of doing it. It's not too involved. This top one here is, I think, the most common way. If you look at an emulator like Vice, a very popular C64 emulator, it's going to look like this. And the other case there, you have a jump table. There's no real big difference here. In both cases, you're looking at like one unpredictable jump somewhere, usually, and then one predictable jump. Like you need to read the opcode and jump somewhere to run the code, and then you need to jump back to the start of the loop again. And so an unpredictable branch is always expensive, or kind of. The predictable branch on a modern CPU is going to be very fast. So the big difference here, and that can be a problem, is that for the jump table, you need to pass state into the function. Whereas if you have all the code inside the switch statement, potentially you can have state on the stack that can be accessed. So that might speed things up. Except in reality, you can't really have, you cannot put the registers on the stack because there's always going to be some code somewhere else that needs that state. So in reality, for the emulators using that switch statement. They usually have global variables for the registers. But of course, if we want to do this in C++, the way I want it, then we need to do a jump table, because I don't want to put all the code inside a switch statement. I want functions that call other functions, so you can abstract things away and make it nice. So this is kind of the main loop with some stuff stripped out, but this is kind of how it looks in my code. Just a while loop. You execute a number of cycles until you're done. You read the program counter. This is the opcode. And then you use the opcode to index into the jump table, and you call the function using reference to this, so you get the state into the function. So let's see. I'm going to try to actually see if we can. Do we have something here? Let's see if we can actually look at the code instead of looking at the slides. Let's hope that. Let's do this. It's hard to see. Okay, so this is, let's go down to the actual opcodes. Should I make this bigger? Where are we? So the whole emulator is in one file. Okay, so this is the opcode table, which is like the main. So this is not a jump table, as you can see. It's you have to create the jump table from this data, but you have the opcode here. And this is a reference to a function, not a lambda or anything, because you can't really. You need to have an actual function pointer. So this is all the. This actually defines all the functions. So if you take a look at the like the LDA that we talked about earlier here. We know that then if we read this opcode, we're going to jump to this function. If we read this opcode, we're going to jump to this function. So it's the same function, just in different template arguments. So here we have it. Load a value from memory into a register. And this sets flags. Flags, this sets the sign flag and the zero flag. So most opcodes in a CPU will affect some set of flags. Like if the value is 0, the 0 flag will be set. If the value is negative, then the sign flag is set. And if it overflows, if you add two numbers together that's too high, then the carry flag will be set. And that way you can make an operation and then you can sort of do something else depending on the result. So you can sort of subtract something from a value, becomes 0, the 0 flag will be set, and then the next opcode can say, if the 0 flag is set, then I want to jump here. So that's how you implement logic. So for most opcodes, you need to both like do the logic, and you need to set, look at what you got as a result, and you need to set some flags from that. So these are, they're function they're const all the way. So, but they are function calls. In a normal emulator, this would be macros, and it goes pretty deep. So you sort of, for those who, I'm not going to explain all this. If you know it, you know it. But it's basically you have to read stuff from memory, and depending on, like you saw the different versions of the opcodes, they need to get the operand. So if you want to load a value into the register, you need to get it from somewhere, and this calculates where in memory you need to get it from. In the simple case, it's going to be right where the program counter is, because it's a constant that lies there. In other cases, you need to read something from memory and then read it back and finally store it in the A register. So I'm not. So the set function, should we look at it? Maybe we should. Maybe we shouldn't, because I can't do it. Jump back to the slides for a bit there. So this, we can skip this because this was the same that I just showed you. But the basic idea here is like we're not going to have a switch statement and put all the code in there. We're going to have proper functions, and we're going to break everything up into functions without sort of messing around. And this is how it looks in Vice. Is a Commodore 64 emulator. It also has a 6502 emulation inside. This is how they do it. To compare, you have macros for everything, calling other macros. So the principle is the same. You can't repeat everything for all the opcodes, but instead of having functions, you have macros that uses macros. And this is a switch statement that runs these things. So what I'm hoping is that Jonas?
It looks like there's a lot more repeating in the Vice code. Is your relation file a lot shorter? Or?
Yes, because you don't have. I have a single load function that does loads for all loads, regardless of the register. The template arguments are the register, that is a target, and the addressing mode. So it becomes a lot more readable and maintainable. Also, like if Vice wanted to run like two emulators at the same time, like say they want to switch between one type of emulation with different settings, that's not really possible here. Right? You have global macros and defines and global variables. You can't do that. But the thing that you might be worried here is like we're calling a lot of functions. They're all const exp, right? So they should sort of just be inlined and it should generate good code, but how can we be sure? And then we come to the second part of this. So benchmarking. I mean, you could just benchmark and see how fast the code is, but I don't really have anything to compare to, and it's hard to know if it's good or not. So I took a different approach here. I used a library called Sidis. This is an x86 disassembler that you can use from your code. So I just included this into my emulator, and it's very convenient because now I have a jump table. So all the opcodes are in an array. So I have function pointers for all opcodes. So the only thing I have to do is iterate through all the opcodes and call the disassembler and look at the instructions. And then I can see, is this good or is it bad? So that's what I did. This takes one function. It goes through all the opcodes, and then I count all the jumps and all the calls. And when I find the return, I'm done. And what I expect here, if C++ does what it's supposed to do, I expect there to be very few jumps and no calls in any of the opcodes. Because if I have a call, then something's gone wrong. I'm going to try one more time here. So I'm going to run this here. And this shows now, for all the opcodes, it shows this is the number of number of opcodes, number of jumps, number of calls, and number of jumps. And this is the total here. So we can see that the average opcodes average x86 opcodes per 6502 opcode is 16. There are no calls, which is good. We have only 3 jumps. It's also good. That means that this looks good. And if we want to investigate a little bit more, we can actually just show the disassembly here. And we need to do this. I don't know what this is something that happened when I tried this recently. There's like a pause opcode. Does anybody know there's like a pause opcode in x86? It seems that for some reason it's put like the first opcode of every. I don't know why that happens. Now we can look at the most simple opcodes are the transfer opcodes. The only thing they do is they move data from one register to another. So TXA, go from X to A, copy X from A, copy A. So these are like, and here you can see these become very simple. Here you can kind of see, so 14 EDI is the this pointer, I guess. This is the machine, the object. Here is the transfer A to Y, transfer, let's compare X to A. So you just have to, you load and store. This is a register, C and 4. This here is for the status register. So there's a trick. I'm not sure if I go into it. Like the status register contains like 1 bit for each flag. So if the result is 0, we need to set 1 bit. If the result is negative, we need to set another bit, and so on, which is kind of involved. And this looks way too little to do that. But there's a trick. All opcodes that affect the flags always affect at least the signed flag and the negative flag. So they always check if it's negative or 0. So what I do in those cases, I don't update the status register at all. I just save the value here. And that means for all those opcodes that only set those 2 flags, which are pretty common, I don't have to sort of update the status register correctly. I just store that value until I need it. And then I, of course, need to sort of use it. But it means that most of the time, you're going to ignore the flags. You do adds, you do shifts, you do all these opcodes, and they set the flags, but you're never going to look at them. So you don't want to spend time actually storing these bits correctly if you can avoid it. But this means we're actually, this is pretty good, I think. So this emulator that I'm testing with, it's compiled with the fastest set of settings. Like it only uses RAM. You cannot map in ROM, or you cannot sort of do anything. That's why it's for a real case, these numbers will be higher. But for testing, I'm pretty happy with that. Yeah, that was it. Okay, so the last point, I said I wanted to be fast and I wanted to be configurable without ifdefs. So this is, I guess, a pattern that at least many of you know about. You use a policy, you have a type with compile time settings and also runtime settings that you use as a template. So the machine is the emulator. It uses a policy as a template, which means that all these settings can be evaluated at compile time. So for instance, we have this function called each op. It is called for every opcode in a loop, which would be very slow, except, of course, the default implementation is to just return false. And that means it will optimize out and do nothing in the default case. Whereas if you wanted a debug implementation where you actually needed to do something for each opcode, like, maybe you have breakpoint set, you want to see, like, is this a breakpoint here, or you want to trace, you want to write every opcode you execute to the standard out, and you need something here, and then you implement this function, and it's going to be not as fast, but you don't pay for it if you don't need it. And there are also other settings here, like I talked about that the test case when I tested disassembly the opcodes, I used the fastest possible access mode. So this defines how we read memory for different types of accesses. So the slowest type of access is callback. That means every time we read a byte from memory, we need to call a function to get the value. And on a normal emulator, you need this because, for instance, from the Commodore 64, if you write to certain addresses like D400 something, you're going to produce sound. Or if you write to the screen, you're going to get graphics. Or if you read from this address, you're going to get a timer value. So in those cases, all those cases, you need to call something that implements that logic. That's the slowest way. Direct access, that means we're just going to read from memory, and we're just going to ignore that there's anything like ROMs or I/O. And what I'm betting, the default settings here is like, for normal writes, we cannot assume that you need to be able to map I/O or stuff into memory, but we assume that when you run code from memory, it's not going to need to do that. We expect you not to put code into the time register and jump there and try to execute them and rely on the side effects for some speed up. But these are also compile time settings, which means that we have here this is the main method for reading from memory. So it checks like, do we have the fast path here? We can just load from RAM. The banked version, that means we need to there's a lookup table for every part of RAM can point to, so you can sort of have things point to different areas. Some memory can point to the same place in memory, which is common. But in the slow case, you need to actually call a function for every access. Okay, so where are we in time? Or less than half hour, okay. So I guess we're at the, any questions, other questions so far? I assume that not everybody is following everything. I hope there's something here. Okay, the next part. Actually writing C++ targeting the 652. Now, why you would want to do that is kind of strange, but it is now more possible than it has been before, because a few years ago there was an LLVM project targeting this CPU again, so it's a pretty decent compiler now that you can use. You can test it on Godbolt, and that's why I was playing around with it. So actually, let's. So I want to just show a couple of examples on. Actually, I can spoil this right now and say that it's probably not a good idea to do this. But I mean, it's a fun project. But the whole idea that C++ will give you kind of zero cost abstractions, and that the code you write there is always going to be almost as fast as what you can do in assembler, that only holds for modern CPUs. It doesn't really hold for these types of old CPUs. So let's start with the most simple, basic function we can think of: copying memory. This is kind of how a simple function would look like. Let's try. Yeah, let's go to Godbolt. Hopefully we can try this here. If I can see it. So the good thing with so here we have the code. Should I make it? Is it large enough? Should I make it larger? It's fine. Okay. Here's the code, and here's you can. There's actually a bunch of them. This is the Commodore 64 target, but there are targets for NES and other weird systems. So the good thing with the modern C++ compiler, it does figure out when you're doing simple things and everything's constant. So like if you're going to copy 20 bytes from one known address to another known address, it knows about this. It unrolls everything, and this is as fast as you can do it. And it actually unrolls pretty far. I think you can go to like 50 or something on 03. Still going to unroll. It's nice. Somewhere here, I think it will stop. But this still looks pretty good. So we have here load from memory plus x, store to memory plus x, increment x, compare to 70, and if we reach 70, if we're not at 70, we will go up again, and we're just going to loop here. The problem here, or problem, but the thing you don't want to pay for here is you do an increment and then a compare. This also sets flags, like I talked about before, but this also sets flags. So what you want to do really is you want to go backwards from 70 to 0, and then you can sort of say that you jump up until x becomes 0, and then you can get rid of one opcode here. But this is still pretty good. So what we can do to try to make this better, we can try to we try to count backwards. We have this one here, memcov3. It just goes backwards. So will it be faster to go backwards is the question. Okay, not really. It actually needs two counters now. It needs to count. It counts down using X, and it counts up using Y to keep track of the loop count. So you can try this a few ways, but it turns out that the kind of the best result is the first result when you're using this. So you're going to have to live with that when you're going to do a straight copy like this. But when you want to copy memory fast, what you actually want to do is you want to copy whole blocks of memory separately. Like if you're copying more than 256 bytes, you want to copy those together. And so this is what you would actually do if you want to copy. Let's copy something like 600 bytes here. Okay, so this is for this amount of bytes. This is actually also almost as fast as you can do it. You're going to copy interleaved, so it's going to like copy 2 bits at the same time. The result is still going to be fine. Here you rely on the fact that you can just increment X until it wraps around to 0, and then you have copied 256 bytes. And then you're done with the whole blocks, and then you also have to copy the rest. So this is pretty good, but this relies on unrolling here. If you look at iCopy, so the number of blocks to copy is length divided by 256 or shift. So, and these are the number of blocks you need to copy. And as soon as you get to like more than 4 blocks, I think it doesn't unroll anymore, and then it becomes bad. So if you go to like 1600, then yeah, this is not as good anymore. But still, for small values, memcopy is. When I tried this, the last time I tried this with like older compilers, you can never get to anything close to this. So, and I think that I don't know if anybody has tried this in C++. I think you can do like manual unrolling by using like recursive templates. Have anybody tried this? Like forced unrolling. So if you want to, the problem here is that if you can actually use the length as some kind of compile time parameter and generate code instead of the loop, I think like a smart programmer could actually write something that does this efficiently. But this is like the simplest case. So the function I really wanted to look at is this here. Put pixel. Write a pixel to the screen. We're going to assume that the screen is actually 320 pixels wide and 200 high, I think, something. And we're going to assume that we're not going to need the right part. It's so hard to use something that's larger than a byte. So we're just going to assume that X and Y are bytes. And to get to the right pixel position, this is what you need to do. So the graphics on the C64, which this is for, is kind of laid out as tiles. So you have this character. So the first 8 bytes are like the first block, and then they go like this. So to calculate the correct pixel, this is the formula you need. You take Y and X, and you get an offset into video RAM, and you OR in 1 bit at the right position. This is setting bit. And again, it's very nice if your values are constant. So if we're just going to set like this, that does what you want. This is the position in screen memory, and it ORs, loads the value, ORs the 4 in, and stores the value. So it sets 1 bit. Perfect. Well, the problem is if you want to actually set something that is not compile time, which is the common case. Well, then it doesn't compile because you have double parentheses. But here, then it gets more complicated. And we also have a jump here to left shift, no, logical shift right. So this shift here, it actually cannot figure it out inline, and it needs to call a function. But what's a bit fun about this, when I tried this like just 2 weeks ago, it had another subroutine call to multiply. So this here, this constant multiplier here, it couldn't do that inline either. It needed to call to a multiplier routine, which is really, really slow. So this is still a lot better, but this is like, what are we talking here? It's like 62 opcodes plus this subroutine call that's going to loop. So it's going to be pretty slow. Now I'm going to do something, see if we can try to actually, can we load this code here? This is some assembly to draw a sign plot on the screen on a Commodore 64. So let's assemble it. I'm not in the right place. I should be here. Okay, so we assemble it. Let's run it. Let's see that it does what we think it does. It ended up on this screen, so we have to go here. Yeah, okay. Nice little sign plot on a Commodore 64. And we can see this is the main code. We clear the screen, we plot the sign, and plot the sign, we loop over coordinates, and we call. Okay, I'm giving the ending away here. This is actually not supposed to be. It should supposed to be this function first. It doesn't matter. So this is my implementation of the plot function. This does kind of the same thing as the generated function, but sort of hand optimized. It's about 30 opcodes instead of 60 something. It doesn't involve a call. So this is a lot better than what the compiler could do. The problem is here, this is still really bad. And this is not how we would do it. This potentially you could, the compiler could get close to this, because this is still sort of figuring out what kind of operations you need to do to actually do a multiplying something with a constant, because it knows that it's a constant. It can sort of figure out the kind of shifts and adds it has to do to multiply with 320. But in reality, plot functions will look like this on a C64. Just these bytes, these opcodes. And what you do is, of course, you use a lookup table. So this is a lambda. You can have lambdas in this assembler, compile time, of course, that does the exact same calculation to calculate the Y offset, also adds the VRAM position. And we create a lookup table for this. And the only thing we have to do, we have X and Y here. We use Y to get the actual position in memory using the lookup table. And we also figure out the mask we need, also using a lookup table, and then we're done. And this is, I think, like 30 cycles or something, 30 cycles, something like that. And no compiler, C++ compiler can do that. It doesn't really do lookup tables. It doesn't work like that, right? And I didn't know if you noticed when we assembled this, it actually said here, test 41,000 cycles. So one good thing with writing an assembler and also having an emulator is that I could actually put my emulator in my assembler. That means I can test code. So I will just have to do this, I think. And then we assemble again. And then we have another test here. Fast plot. Takes 35 cycles. That's pretty good. We can compare it to then this more traditional plot. And we assemble again. And that's 90 cycles. So and this is, I would guess, and I can't really measure the generated version on Godbolt, but I guess that would be at least 200 cycles, because it's twice the number of opcodes plus a subroutine call with a loop. So the takeaway here is, of course, that it's fun to play with, but you can't really write optimized code in C++ for this CPU that's almost 50 years old. Yeah, I had a lot of slides in case I couldn't do this, so we can. Let's go back to the slides. Can we do that? Here. Yeah. Where is my mouse pointer? There it is. Yes. So this is the same. This is actually how we can. In my assembler, this is how I implement memcopy in the assembler with macros. So here we're saying like, if the areas don't overlap, we can do the fast copy. This is when you do the interleaved copy that I was showing before, because you need to make sure that if they're overlapping, you can't do all this fancy stuff. And the fast copy does kind of the same as the iCopy version I showed in C. It calculates the number of blocks to first copy, and then it copies blocks with a repeat, and then it copies the rest. So this will generate like the optimal assembly, more or less, for copying memory. And this was a bit pixel. This was the old. Can you see the jump to the? Yeah. Yeah, maybe you can see. But this was when I generated this slide a while ago. There was a jump to multiply high 3 here. So they've already improved the compiler enough to get rid of that. That's nice. Yeah. Okay. Yeah. We have one extra thing that we can talk about, which mruby. Who knows about mruby? Just Harald, almost. Mruby is an implementation of Ruby used for embedding. So it's like a more lightweight, but almost feature full. And you can link it into your C code and run Ruby programs. And of course, Ruby also compiles to opcodes and executes them, very similar to an emulator. And if you remember when I said that there were like only 2 basic ways to implement a machine like that, you need to do a jump table or a switch statement. And in both cases, you had one unpredictable jump and one predictable jump. That's not actually true. Has anyone heard of this concept? Do you ever? Okay, some people. So this is threaded here does not mean threading. I think this concept is older than threading. So if we actually look at the core of the mruby source code, this is the function that runs opcodes in mruby. I've stripped away some things here, of course, otherwise it would be impossible. So here is the main loop for executing opcodes. Macros again, of course, it's C, it's macros, it's always how it looks. But I would assume from looking at this that this macro would be like a for loop and a switch statement. And case here would just be case in the switch statement. Next would be break. And end dispatch, I don't know what that equals to, but this is what I imagine the default case would be for these defines. And if we look at the default case here, that's kind of how it is. Init dispatch does the for loop, reads the opcode, does the switch, and in the case instruction, it just increments the program counter. And I don't really know what this fetch op stuff does. Next, it's not break for some reason. It's actually go to end, and then this end dispatch defines this label. So instead of breaking, it actually jumps out of the loop, or to the end of the loop, I should say. But this is when direct threaded is not defined. So the question is, if you have direct threaded defined, what does it do then? Okay, so init dispatch does next, and then return. There is no looping here at all. Well, we have instead the case statement, increments the program counter. It seems to do about the same. The next statement does not break or jump. It reads an opcode and jumps to the opcode through a table. And so what's going to happen here, the opcode is going to execute, and after the opcode is run, it's just going to read the next opcode and jump to it. So there's no looping, there's no switch statement. It's going to execute the opcode, and it's going to directly jump to the next opcode to that label. So this op table here points to all these labels. So here we have one unpredictable jump and no predictable jump. There's only one jump per opcode. So this is an interesting optimization. I don't know how much this will help on the modern CPU. Like I said, predictable branch costs almost nothing, but it's still an interesting technique, I think.
Is that the GCC extension, the go-to
A label inside an array. But I've compiled this. Well, no, this is compiled with its own systems. I don't know. So threaded here means that it's threading the opcodes after each other instead of sort of going down, taking an opcode and going up again. It's threading through. And I think that's it for me, for now. Any other questions? Did you understand something? Yes?
Does your emulator run on a C64 and using the compiler? You can compile your emulator to assembler for the C64, right?
Okay, and well, those kind of, some people like those kind of weird things. I don't know if you saw this news lately that they managed to run Linux on the C64. It takes like 7-8 hours to boot to the prompt. But I guess if you can do it. Yeah.
Did you think about like adding the simulator for some reusable like softwares, emulation softwares like QEMU?
For what? For
QEMU?
Yeah, I don't know. I don't think it's. I mean, there's so many emulators. The nice thing with this is that I can, like I said, I can put it into an assembler. It's very easy to use for it. But in QEMU, that's like a system by. I don't know if you. That would be if you sort of have some kind of hardware project that you would want to emulate or something. I don't know. I'm not very familiar with the QEMU. Anything else?
Okay. Thanks, Jonas.